Alright, so now we're going to talk about video 2. What do we do with this, okay? How do we use these numbers of charge of an electron, charge of a proton, the Coulomb, alright? And we use Coulombs Law to calculate electrostatic force, okay? Force between charges. Okay, so let's look at it qualitatively first, okay? Meaning, we're not going to plug in any numbers here. Okay, so let's say I've got a Coulomb of charge over here and a Coulomb of charge over here. Okay, you could picture it kind of like with the balloons. Alright, charge sitting kind of centralized somewhere. Alright, what if, and they're some distance r apart as well. Okay, what do you think is going to happen if I double one of the charges? So I take one balloon and put 2 coulombs on it. What do you think is going to happen to the force?
Double?
It's kind of like what we did with gravity, right? Okay, if we double this, what happens to that? Okay, it is going to double the force, all right? So we're going to get double the force over here on this charge, right? Okay, now Newton's third law says that if this force gets doubled, doesn't this force get doubled as well? Okay, so here is a huge thing that you get tested on all the time is Newton's third law applies here, even though we're talking about charges. Okay, we already know that if we step with 15 newtons of force pushing back that way, doesn't the Earth push us forward that way with 15 newtons of force? Newton's third law. That's how we get around, okay, friction, all that. Same thing applies here, okay? It's just with charge. All right, what if we double both of them? How will that compare to the original force that we had? So here we had force F. We are doubling everything, so we are going to get 4 times quadruple the force, okay? All right, what if I triple one and quadruple the other? 12 times the force I had before. Okay, the point of this is to say that both of the charges matter. All right, both Q values. We abbreviate that Q. Okay, so we can say in our notes, force is proportional to Q1 times Q2. Okay, now we talked with gravity, did we talk about if we shined a light off in space, okay, what will happen to the intensity on the paper, okay? And then we talked about how gravity relates to that. We said that as the astronaut gets 1, 2, 3 times, okay, plus we got to include the radius of the Earth as well, so 4 times as far from the center of the Earth, what happened to their gravitational force?
4 squared.
It decreased by a factor of 16, okay? So we only increased the radius by a factor of 4, but gravity went down not by a factor of 4, but by a factor of 16, because why? What do we have mathematically in the big G equation? Radius squared on the bottom. It is an inverse squared law, okay? Coulombs law, it's also an inverse squared law. Okay, so let's look at this. Now, we're going to put a bunch of charge there, all right? And we are going to take a little test charge and we're going to talk about how much force is on it. Okay, now you notice here on this slide, this is not an attractive force, this is a repulsive force, okay? That thing does not want to hang out with that thing right there, okay? Repulsive force. So it's still going to go down by a factor of 16 if we quadruple the distance, okay? So we can say that force is proportional to 1 over the radius squared. Okay, now let's put these two things together. We have these two things, all right? If we put them into one equation, we get that. but it's not really an equation yet because we're missing something. Okay? And it turns out if we multiplied the two charges divided by the radius, the force would come out way too small this time. Okay? Electrostatic force is way, way, way strong. Okay, look at the constant. Constant is little k instead of big G. And the value of the constant is this number right here. Okay, but don't write this down.
Right.
Okay, we're going to make it easier. So this whole thing, it's convenient to round it to 9. So it's 9 times 10 to the 9th. Alright, now what was big G measured to? .67 times 10 to the... Okay. -11, right? This one's to the 9th, okay? So this scales up electrostatic force a lot. Alright, so let's look at this. We can compare the two. They're both calculations of force. Okay, they both depend on the product of either mass or charge, inverse square laws. Okay, but that one's to the 9th, that one's to the -11th. Okay, and it kind of tells us this: electrostatic force, very, very strong. Gravitational force to the -11th. Okay, very weak. Okay, so let's do a couple example problems. In a minute, we'll play with the Van de Graaff generators. It'll be in the video 3. Okay? You can charge Van de Graaff generators up. Okay, so let's say we're able to charge one up positive and one up negative. There's going to be an attractive force between these two. Okay, so that's a big difference between gravity and electrostatics. Gravitational force can only be what? Attractive, right? Okay. Electric force can be attractive or repulsive. Okay. Eventually those are going to jump over there. On the left one we've got 0.00025 coulombs. On the right one we have 0.000017 coulombs. Let's say they're 1.31 meters apart. How much electrostatic repulsive force? Okay, set that up on example 1 on your notes there. And punch it into your calculator. Okay, so if you do this, you should get about 22 newtons. Alright, yep.
Why wouldn't you have to 1.31 and half to get a radius? Are you just assuming the whole thing?
It's distance from center to center. Yeah. Yep, radius is center to center. Okay, any other questions? Let me switch the screen to my work over here. Alright, so here's how you're gonna plug it in. Common mistakes, not squaring the bottom, maybe. Forgetting to square that. Not using the E key in your calculator. Might mess something up. Okay, maybe some order of operations, something like that. Okay, we've done a lot of calculations like this, so it should be fairly easy, right? Okay, example 2. This one I'm going to have you guys solve for something a little bit different. All I want you to do right now is list the data, and then we'll try this on our own later. Okay, so let's change some things here. We're going to keep Q1 and Q2 the same. So write that down. Q1, 0.00025. Q2 is 0.000017. And capital C is the abbreviation for coulombs. Alright? Okay, so how far would these two charges have to be apart to have an electrostatic repulsive force of 1,000 newtons? So this time I'm giving you F. So put F equals 1,000, and this time I just want you guys to solve for R. Alright, any questions on Coulombs Law? Okay. Alright, Devin, you can shut that one down.